So this is our last section in chapter 2 of our textbook, which talks about variations. Variations is some applications, and let's just read through this. I'll show you how to set things up and how to easily do these. So these to me are some of the easier word problems that you may find. And so there's different types of variation problems. One is a direct variation, and this is where one variable is a constant multiple of another. I'm going to read through these and then we're going to look at how to set these up. So if you have an inverse or indirect variation, this is where when one of the variables increases, other one decreases. Their product is constant. All of these have some constant, and we usually denote it by the letter K, and we'll do that in a second. Joint variation, this is where more than two variables are related directly. Combined variation, this is which involves combination of direct and joint variations and indirect variations. Okay, so let's look at direct variations and how we would set up that formula. So direct variation, and sometimes they are actually called proportional variations. How we set this up is y is equal to k times x. Again, k is equal to some fixed constant. Okay. Notice there, if I have y is equal to k times x, if I divide both sides by x, I get that k is equal to y divided by x. And so this is why that other formula is in there. And this is just saying it depends on which point you're using. Okay. But you get the same thing. So the value of y varies directly with x. Y is directly proportional to x. K is called the constant of the proportionality. Special cases, direct square variation. So if it said y varies directly with x squared, we would write this as y equals k times x squared. Basically, in these word problems, we're going to get a sum statement, and we're going to be able to write out what that direct variation is, or whatever type of variation it is. And then it's going to give us information about values of our variables so that we have enough information to figure out what that fixed constant k is. And then they're going to give us other information that we can answer. If we're talking about inverse or indirect variation, the way that we write this is y is equal to k over x. We could solve for k right there by multiplying both sides by x. So what this would say is the value of y varies inversely with x, or we could say y is inversely proportional to x. Y is indirectly proportional to x. Again, y is equal to k over x is how we would do this. If it said indirect square variation, then y is equal to k over x squared. Joint variation, that means that we have more than one variable in there. And so looking at joint variation, like direct variation, but involves more than one variable. So for instance, y equals k, that constant, times maybe x times z squared. And how you would write that, y varies jointly with x and the square of z. And then a combined variation. This involves a combination of direct variation or joint variation and indirect variation. So for example, y is equal to k times x times y all over z squared. And how we would say that is y varies jointly to x and w and inversely as the square of z. Okay, so this is how the terminology and how we're going to help us set up these word problems. So just so it kind of makes it so it's not so intense. And just look at these real life situation. So these sound like a lot of fancy math words, but it's really not too bad. And here are some example of direct and inverse variation. For instance, the number of dollars I make varies directly, or I can say varies proportionally with how much I work. And K is the positive. So in that case, K is my hourly income. X would be the number of hours I worked. Another direct variation, the length of the side of a square, that varies directly with the perimeter of the square. Example of inverse variation. I said the number of people I invite to the bowling party varies inversely with the number of games they might get to play. So inverse, another way to state that is you can say it's proportional or inverse of. Another example of the inverse correlation is the temperature in my house varies indirectly, same as inversely, with the amount of time the air conditioner is running. And last example, inverse, my GPA may vary inversely with the number of hours I watch TV. Okay, so let's look at a few easy situations where all we're doing is going in and writing the formula out. So we're not even solving anything. We're just figuring out what the formula is going to be. We have some problems in front of us. So C says, or number 1 says, C varies directly as A. So C varies directly. So that tells me I need the equal sign and I always have this constant K in here. And it varies directly as A. So C is equal to K times A. The next example says, X is jointly proportional to Y and Z. So X is jointly, so that means X is equal to K times, it's proportional to Y and Z. So Y, so K times Y times Z. If it says W varies inversely. So right there, I know W is equal to K inversely as X. So this is all over, K is all over X. I'll give you guys a second, just in case you're trying to copy all this down. So the next one states R varies directly. So R varies. So R equals some K. So it varies directly as a square of S. So times S squared. Five says F varies jointly. So F equals K, and it's jointly as X and Y. So that tells me I'm multiplying K times X times Y. Number 6, J is inversely proportional. So J equals inversely. So I need the K, and that means I'm going, K is over. So it's inversely proportional to the cube of M. So all over M cubed. If it says H is directly proportional, so H equals K times, it's proportional to B. So K times B. There's one more. And this one states X is jointly proportional with the square of A and the square root of B. So X is jointly proportional. So I know X is equal to, I always have that constant K, with the square of A, so times A squared, and the square root of B, so times the square root of B. Okay, so our word problem is always going to have something that's going to help us set up the word problem, where we're going to go in and we're going to write out the equation that we're given. Then they're going to give us some information again about our variables so that we could figure out what that K value is representing. Oops, I thought I was done, but I'm not. So there is one more. A is inversely proportional to B. So A equals, so always have that K value, proportional to B, inversely proportional. So that means I'm going to go over K all over B. Okay, so the next examples, I don't know if I'm going to go through all of them because I have quite a few, but the next examples, we're given, again, enough information that we can figure out what that constant of that variation represents. Okay, so direction says find the constant of the variation and write the formula to express the relationship using that constant. Okay, so first piece, we're going to set up the equations like we were just doing. So it says A varies directly as B, and A equals 15 when B is 5. Okay, so let's first set up our equation. A varies directly as B. So A is equal to K times B. So now we have enough information that we can figure out what K is, because we know that when A is 15, then B is 5. So we have 15 is equal to K times 5. So now we can figure out what K is. Divide both sides by 5, we get K is equal to 15 divided by 5, which is 3. Not 3. 15 divided by 5, which is, yes, 3. Okay, so we know what K is. They want us now to write this formula with the value of what we found K to be, because that's always going to be the case for this setup. So A is equal to 3 times B. So the next example states that P is jointly proportional to Q and R, and P is equal to 12 when Q is 8 and R is 3. Okay, so first we're going to go through and we're going to set up our equation. So P is jointly proportional, so is equal to K times directly proportional to Q and R. So K times Q times R. So now we're given enough information so we can figure out what K is in terms of this situation. So we're given that P is 12. So we have 12 is equal to K times Q, but Q we're given is 8. So K times 8 times R, and R we're given in this case is 3. So now we can solve for K. So we get 12 is equal to, well, 8 times 3, that's 24 times K. I just like the K after the number. Get K by itself, we can divide both sides by 24. And so we get K is equal to 12 divided by 24, which reduces to 1/2. So now we're going to go back in and we're going to substitute in what K was. So P is equal to 1/2 times Q times R. So I'm going to let you guys try it. Why don't you guys try the next 2 problems? I'll pause the video in a second and I'll let you guys try it and then we'll go over it. So let me just read them to you and then I'll pause the video. So the next one, number 12, in this case says C varies inversely as D and C equals 7 when D is 4. The next one says T varies directly as the square of U and T is 6 when U is 3. So go ahead and try those. I'll pause the video and then come back and we'll talk about it. Okay, so I got feedback. You guys had a chance to work on it. And let's just quickly go through these. It says C varies inversely. So C equals K. Inversely as D. So K is over D. We know that C is 7. So 7 is equal to K all over when D is 4, all over 4. And so all we have to do to solve for K is multiply both sides of our equation by 4. And so 7 times 4 gives us back 28. So I just had you guys give me what the K value is, but they did want us to set this up. So setting the equation up with what K is, we get C is equal to 28 all over D. So this next one is where some of you are off. And it says T varies. So T equals directly, so K as the square of U. So times U squared. And T is 6. So 6 is equal to K when U is 3. So 3 squared. I think some of you, got the square, didn't do the square. Maybe not. No, that's not right. So we get 6 is equal to K times 9. So to get K by itself, we're going to divide both sides by 9. And so we get K is equal to 6 over 9, but that reduces. 3 goes into 6 2 times, and 3 goes into 9 3 times. So K is equal to 2/3. To set up the equation, we have T is equal to 2/3 times U squared. Okay, so hopefully, if you didn't get it correct, you found out or saw what you had done wrong in your example when you're trying it. So let's just do a couple more and then let's move into some word problems. So setting it up first, it says A is jointly proportional. So A is equal to K. It's directly proportional with the square of X, so times X squared, and the square root of Y, so the square root of Y. So we have our setup of our equation. It tells us that A is 25. So we have 25 is equal to, okay, X is 5. So all times 5, but we square X. And the square root of Y, and Y is 9. So let's first simplify the right-hand side. We get 25 is equal to K times, well, 5 squared is 25, times the square root of 9, but square root of 9 is 3. So 25 is equal to, excuse me, 3 times 25, which is 75, times K. Let's divide both sides by 75. So K is equal to 25 over 75, but that reduces, both of them have 25 in common. So K is equal to 1/3. So our equation is A is equal to K, which is 1/3 times X squared times the square root of Y. Okay, so maybe you guys try one more. So this one says M is inversely proportional to N, and M is 1.8 when N is 2.1. So I'll give you a couple of minutes, try it, see if you can get it. Okay, so M is inversely proportional. So M equals K over, because inversely, to N. So K over N. We know M is 1.8 is equal to K all over N, which was 2.1. So I can see K is equal to 2.1 all times 1.8. So I was just saying with a video on that you guys should be able to do this without a calculator. So let's just multiply 8 times 2.1. So 8 times 21. So this is 8 times 1 is 8. 8 times 2 is 16. Going over another digit, so to multiply, so I put a 0. So 1 times 1 is 1. 1 times 2 is 2. Add my digits. I have 8, 7, 3. And then figure out where I put my decimal. I have 1 spot here, 1 spot here. So I have to move it over 2 spots and I get 3.78. So our equation that we have is M is equal to 3.78 all over N. Okay, so the next problems, we're going to solve each of the following variation problems by setting up the formula to express the relationship. Then we're going to find the constant, that constant K, and then we're going to answer the question. So our first example is the current of an electrical conductor The current of an electrical conductor varies inversely as the resistance of the conductor. If the current is 12 amps when the resistance is 240 ohms, what is the current when the resistance is 540 ohms? Okay, so let's first go through and let's first set up the generic equation. And it looks like we're going to need to define what variables represent. So the current of the electrical conductor. So maybe let C equal the current. Of the electrical conductor. So right now we know that C varies inversely. So C is equal to K all over. It's inversely with the resistance of the conductor. So maybe let R equal the resistance. Of the conductor. So C is equal to K all over R. Okay, so we set up our equation. And the next bit of information is going to give us enough information to figure out what K is. So it's telling us if the current is 12, so we know C is equal to 12 when the resistance is 240. So this is when R is equal to 240. So we're going to use this to figure out what K is. So I know I have 12 is equal to my K all over R, which is 240. So we can solve for K by multiplying both sides by 240. So I get K is equal to 12 times 240. So if we multiply that out, we should get 2,880. Okay, so we now know our equation and we can answer our question. So our equation that we'll be using is C is equal to our K value, 2,880, all divided by R. And now we can answer the question set, which says, what is the current when the resistance is 540 ohms? So we want to find the current, we want to find C. When R is equal to 540. So C is equal to 2,880, all divided by 540. I see that this reduces at least 2 goes into both of those. So 2 goes, well, 10 goes into both of those. And then 2 goes into 288, that's 144. 2 goes in there 27 times. They both have 9 in common. So 9 goes into 144. 16 times. And 9 goes into 27 3 times. And so our current is C is equal to 16 thirds or 5 1/3 and we're in terms of amps. So at first they can look kind of tricky and hard, but if you just break it down like we were doing, it's actually not too bad. Okay, so the next example says the number of aluminum cans used each year varies directly as the number of people using the cans. If 250 people use 60,000 cans in 1 year, how many cans are used each year in Dallas, which has a population of 1,008,000? Okay, so I go through this and I'm going to first pick out what my equation is, and it says the number of aluminum cans used each year varies directly as the number of people using the cans. So maybe N equal the number of aluminum cans used. Each year. And maybe we can let P equal the number of people using cans. And so the number of cans and used each year varies directly equals K times the number of people using the cans. So K times P. So now we have enough information to figure out what K is. We have 250 people. So this is our number of people. Use 60,000 cans in 1 year. So this is our N value. So we have 60,000 is equal to K times P, which was 250. So I can see that K is going to be 60,000 divided by 250. So to save some time, let's just plug in the calculator. So 60,000 divided by 250. That gives us 240. So K is equal to 240. So now we can set up our equation to answer any question about the number of cans used in the year. So we have N is equal to K, which is 240, times the number of people, P. So we want to know how many cans are used in Dallas each year. So we get N is equal to our 240. And it told us that Dallas has a population of 1,008,000. So we need to take our 240 and multiply it times the population, 1,008,000. If we do that, the number of cans that we get we have 2, 4, 1, 9, 2 with 4 zeros. Let me just put my commas in there so I can read that off. So that's 241,920,000 cans. Used in Dallas each year. Okay, so one more example. The weight of an object on Mars varies directly as its weight on Earth. A person weighs 95 pounds on Earth, weighs 38 pounds on Mars. How much would a 100-pound person weigh on Mars? Okay, so we know that the weight of an object on Mars varies directly with the weight on Earth. So maybe M equals the weight on Mars. Maybe E equals your weight on, or the weight on Earth. Well, it says M varies. So M equals K directly with the weight on Earth. So equals K times E. We now know that a person weighs 95 pounds on Earth, weighs 38 pounds on Mars. So we have 38 is equal to K times 95. So K is equal to 38 over 95. So K is equal to 0.4. So we now know the weight of a person or an object on Mars is equal to 0.4 times the weight of the object on Earth, E. So now we can answer the question. So how much would a 100-pound person weigh on Mars? So M is equal to 0.4 times 100. Okay. So M is equal to 40 pounds on Mars. Okay, so a 100-pound person would weigh 40 pounds on Mars.